In this video, we'll be demonstrating how to implement multiple linear regression in R. To do this, I'm going to use the NFL Draft dataset from the BSDA package. Now I'm going to predict a player's draft rating based on their 40 time and weight, and I'm going to use a multiple linear regression to do this at the same time. So I'm going to fit my model, which gives a model without interaction, and we're not going to touch on interactions in this video. We'll get to them in the next one, or in the next chapter, excuse me. But all I do to fit a model with multiple independent variables, a model that doesn't look at the interaction between multiple independent variables, is to just use the variable name of the first variable and then the plus sign to indicate that I want to add another independent variable, and then the variable name of the second independent variable. And I could keep doing plus another variable name plus another variable name for as many independent variables as I'd like to include. Now, just like normal, we're going to first check the assumptions. So the first assumption that I'm going to look at is the relationships between my variables. It's a good general thing to look at. Now, what I like to use is the pairs20x function from the S20x package. This gives me a histogram of each of my variables, as well as the scatter plots and low S curves, regressing each of these variables on each other and looking at the relationship between them, and the correlation between these variables. So I can see that 40 time and weight have a moderate correlation between them, but that 40 time and rating don't have a particularly high correlation, and weight and rating don't have a particularly high correlation, nor do they seem to have a particularly strong linear relationship. Note that this is not a violation of linearity. What I do for a violation of linearity is look for nonlinear relationships. Here I'm just not seeing anything particularly strong, and my statistical model will check if there is a strong enough linear relationship to be considered statistically significant. Now, because of the moderate correlation I see between my two independent variables, 40 and weight, I really need to check before I interpret any parameter estimates that the independent variables are not too closely related. And recall how we check this is using the VIF function from the CAR package. So I'm going to take my statistical model, put it in the VIF function, and then I see that the VIF for both of these variables looks good. Note that the VIF values, if I just have two independent variables, are going to be the same for each of the independent variables. And these look relatively good. Again, depending on what criterion you use, I'd be concerned if it were maybe more than 3 or more than 5. If it were more than 5, I might try to see if there's something I could do to fix it. Though, depending on who you ask, you could go maybe all the way up to even 10, let's say, if it would have to be more than 10 to be fixed. All right, well, that's multicollinearity, and again, that looks pretty good, even though we had a moderate correlation and a reasonable linear relationship between our two independent variables. VIF indicates that that's not a particular concern, so I'm going to move on. Independence, I can just graph these in order. Now, it does look like there's a violation of independence here, so I'd have to go and check on that with the research team to figure out why does it look like these ratings decrease in these little chunks. This definitely looks like a violation of independence. But for this example, let's assume I went and talked to them and they said, oh, well, we ran the greater ratings to the lesser ratings of this position, running backs, and then linemen, and then, or excuse me, centers, and then guards, and then tackles, so different types of offensive linemen, and that's why these are related in such a way. And I could look at that and say, okay, that doesn't seem to have anything to do with my relationship between rating and, or excuse me, 40 time, weight, and rating. So I'm not going to worry too much about that. But this is something where if I saw this in a research study, I would definitely pause, go look at, and ask them about that. In this particular case, if what I had just described were true, maybe what this would indicate is that I need to take into account another independent variable, that being what position that player is on the team. Anyway, for this case, I'll just move on. So let's check normality. Now, normality, again, we're looking at the residuals of the model. This normality plot looks just fine. I could have done scale resid mod and then AB line 0, 1, but this line works okay. This is the default line that R uses. It can be a little deceptive sometimes, so I think normally we use the AB line, but this works here. It's a little bit of a quicker way to do it. Then I can look at the residual plot, checking the homogeneity of variance and linearity. Now note that I can't really use scatter plots anymore because this is multiple independent variables. So I could kind of look at those and see if those are related, but those don't really help me in determining joint nonlinear relationships. So this is actually the plot we end up using to determine if there's any real challenges to linearity. Here, homogeneity of variance looks reasonably fine. There doesn't appear to be any large issues and no large issues with linearity, so our assumptions are absolutely okay. Based on this, we can go on and look at parameter estimates. So the model, you can see that I now get parameter estimates for beta 0, beta 1, which is the coefficient of the independent variable 40, and beta 2, which is the coefficient of the independent variable weight. Running my summary, you can see that I get the coefficient estimates, the standard errors, t-values, and p-values. All of these are what are typically reported in tables when I report my results in a write-up. Now, interpreting these real quick, the 40 time is -2. Well, first of all, interpreting these, I first need to check, are they statistically significant? So in this case, both of these are statistically significantly different than 0, and this is an important consideration that some students forget. Statistical significance from 0 indicates whether or not I can interpret these as the numbers they are, or if I have to assume that these values are 0. Note that if I don't have statistical significance, I assume these values are 0, and thus assume that this independent variable, or whichever independent variable without statistically significant relationship, isn't related to the outcome after accounting for the other independent variables. Now that I've determined that these are statistically significant, I can look at these. Looking at this 40 time, I see that it's negative, so as 40 time increases, the rating of the player decreases, which is exactly what I would expect. Now, 40 time increasing by a second, if you think about what does that actually mean, it's very, very rare for 40 time to increase by a whole second. That's a pretty major shift, even though it may seem pretty small. So 40 time increasing by a second, which is a pretty major increase in 40 time, results in a roughly 2 to 3 point drop in the rating of the player after accounting for the player's weight. So that's the new thing that we have in our interpretations here. Then vice versa, an increase in weight of a single pound slightly increases the player's rating after accounting for their 40 time. Now note that the weight increase for a single pound doesn't actually make a whole ton of sense, because we wouldn't expect a single pound increase to really change the nature of a player who we're looking at their rating for. So I might look at maybe 10 or 50 or even 100 pound difference in a particular player. If I were looking, I'll just look at a 10 pound difference. Now, if I'm looking at an increase in weight of 10 pounds, I multiply my parameter estimate by 10. That yields a 0.16 increase in their player rating for an increase in weight of 10 pounds, a 0.16, again, just multiplying this parameter estimate by 10, which is not particularly high. I'd have thought that I frankly would have thought that as a player gets heavier, they might be less useful, though in an offensive lineman, you might want heavier players to be able to push people around a little bit more. But especially for something that's statistically significant, the size of this effect doesn't seem to be particularly large. And actually, this brings up a larger point with statistics, that sometimes we have statistically significant effects, but the size of the effect isn't particularly meaningful. So this can be something that might be statistically significant, but practically might not be significant at all. Even if you gained 100 pounds, that's like a massive, massive, massive change in a person's physical profile. Your points would only go up by 1 point in your rating. So a relatively small change for such a massive change. For a more reasonable change of maybe 10 pounds, you'd only go up by about 1/10 of a point, or 0.1 to 0.2, so a tenth of a point to 2/10 of a point, which is I don't know much about NFL combine ratings, but seems pretty darn small to me. Again, all of these interpretations are after accounting for an individual's 40 time. So I'd call this one, based on my knowledge of individual ratings for NFL players, probably an effect that's statistically significant, but practically maybe not that impactful. And again, I'd need to go beyond saying, oh, look at how small this is, because a change of weight of 1 doesn't really mean much in context. And thinking that this parameter estimate is small in that scale just demonstrates that I'm not really thinking of the problem, because of course it's going to be small if I'm only changing my weight by 1. So what I need to do is work through this and figure out, okay, so for a reasonable change of weight that I'd actually be expecting something to happen, what would that be? If you have no idea what a reasonable change in the independent variable is, you could always look at the range of the independent variable, look at the mean and standard deviation. We kind of demonstrated this in our slides. You could look at the mean and then the mean plus 1 standard deviation, or the mean minus 1 standard deviation, to look at a couple of different values and see, well, what if I went from 1 standard deviation below the mean to 1 standard deviation above the mean? How much would that impact the independent variable? Or excuse me, how much would that change impact the dependent variable on that scale? And that would be a good way to walk through this if you wanted to. All right, so in addition to running that, we can also run the ANOVA table, as I mentioned earlier. The ANOVA table that R spits out, it breaks the sum of squares for the regression model down into the different components that make it up. So you could kind of combine these back together and create the sum of squares regression if you wanted to. But R breaks them down by default. Note that I'm not using the built-in ANOVA table. That does something that we don't tend to like, which is not the test for the last variable in. It tests for the first variable in, or excuse me, it tests for the variables entered in the order in which you write them, which is a very, very different statistical test that's a little bit confusing. So if you're running an ANOVA model for the linear model, I'd highly recommend using the capital A ANOVA from the CAR package. And then you can leave it by default, or you can use type equal to 3, which is what I'd tend to recommend. All right, so for prediction, well, for prediction, we have to give it values not just for one independent variable, but for all of the independent variables that we're looking to do the prediction. So in this case, I'll try to predict the rating for an individual whose 40 time is 5.55 and whose weight is 280 pounds. So my prediction for their score would be anywhere between a little below 4 and a little below 6. So about 4-ish to 6-ish would be my prediction for the mean response given this 40 time and the weight. So if I had a whole group of people who ran this 40 time at this weight, this is where I'd expect their mean rating to be. Now for an actual prediction interval, I have a single person who just ran a 40 time of this and a single person who had this weight. And again, these are for the same person. So a single person who weighed 280 pounds and just ran a 40 time of 5.55. If I were trying to predict what their rating would be, it would be this that's given by the prediction interval, which looks like it's between closer to 3 and then about 6.5. Now recall that we don't want to do predictions when our values are heavily extrapolated from our data. So we need to check the distribution and the values for our 40 time and our weight. So looking, I use the 40 time of 5.55, which is within the range of the 40 time, and then I use the weight of 280, which is within the range of the DAT weight. So both of these x values are within the range of the x values, so it looks like we're not particularly extrapolating in this case. But as we talked about in the lecture slides, we have to be careful about using univariate methods to assess extrapolation in a multiple linear regression. So what we need to do instead is to look at the joint distribution. So I'm going to graph a plot. This is the joint distribution of my independent variables. This isn't x versus y. This is my independent variables. And again, I'm using this to determine extrapolation. So this is roughly the kind of where my data are being covered. I'd call this point and outlier. So my data being covered is really down here. This is where I'm getting data coverage. So anything not kind of within this rough circle is going to be extrapolation. So I'm just going to add the point with my x value and my y value and color it red. And I see that the point that I'm actually predicting here is this value that's well outside of the joint distribution of my x values and y values. So this is a great case where if I looked at if I looked for extrapolation univariately, I would check my range of the x variable 1, which is the 40 time, range of the x variable 2, which is the weight. I'd see that my values for each of these univariately fall within the range of those values, which would normally indicate a lack of extrapolation. However, this is a case of the quote-unquote hidden extrapolation, because when I look at the joint distribution of my data, I can see that this value, this red value here, is not close to any of my other data values that I have to base my model on. So really any predictions that I make with this data or any other data point that falls outside extrapolating from our x values really isn't supported by my model. It doesn't mean that the prediction is wrong. It just means that the prediction isn't supported by my model because I never looked at data from individuals who had similar characteristics to the individual that I'm trying to make the prediction for. So this has been how to implement some multiple linear regression in R, including how do we check the assumptions, how do we look at the model, how do we look at the ANOVA, how do we run the predictions, and then how do we check for that hidden extrapolation by checking the joint distribution among a couple of independent variables.